All right. Today I've got some questions I want to go through for stage 2 physics. We've got some questions on electric and magnetic fields from topic 2. So let's have a go at them. All right, so I've got some scans of the questions and I've got started with some of the worded answers already to save a bit of time of me typing. All right. So first question, one way to focus electrons in an electron microscope, use two triangular uniform magnetic fields of equal magnitude B, diagram below. You can see we've got fields coming out of the page and fields going into the page. And these powerful electrons that seem to bend into a focus into a point. Right. When electrons in the magnetic field, they travel with uniform circular motion r. Explain why an electron moves with uniform circular motion when it enters the magnetic field with velocity perpendicular to the magnetic field. Okay, so main kind of idea of uniform circular motion is you need to have a force that always acts on a right angle to the velocity, and that's what the right-hand rule says. Your right-hand rule states the direction of force is always at right angles to the direction of velocity current. Is actually against it because it's an electron, so you reverse the direction of your force, but that's still right angles. So if there's no component of force that's in the same direction or opposite the direction of the charged particle, or any object for that matter, if there's no component of no parallel, anti-parallel component, then you can't speed up or slow down, you can only turn. And that's what we observe. Okay. All right, derive the equation mv equal mv on br. Yeah, okay, so radius equation, magnetic field. Now, I did actually put, what did I do with it? So I've got a formula sheet here in case we need it. I'll just go and talk about the key components we will need for this. So we're going to need the centrifugal force formula, which is, that times mass effectively. Okay, so it's mv squared over r. And then we're going to need this one with sine 90 equals 1. So, all right, the equations we'll need, I'll just draw them in. All right, so we have force centrifugal equals mv squared over r, which is going to be equal to, is what this is being provided by. Something's going to provide the centrifugal force, in this case is magnetism. It equals B V Q. Okay. Now, these can be cancelled out straight away. Okay. I'm going to multiply my R across the other side. And V equals BQR. Then finally swap the sides and divide the B and the Q across. R is equal to M V over BQ. Okay, so that's what they're looking for. You can't start with the equation and work backwards. You're going to have a hard time doing that anyway. But if you do that in the exam, you'll get no marks for the attempt either way. Okay. And now we're going to use this one. All right, so we've got magnetic field magnitude. We should have got my calculator before this. Let's load that up now. Magnetic field, okay, and radius of path of r equals that distance. Hence, show the magnitude of the momentum magnitude. Okay. Okay, magnitude. Okay, so we can work out we've got the mass. Okay, why? Okay. Well, basically, we can just rearrange that formula. It's not quite used to doing it this way. We can work out the formula basically to work out the velocity by just going back to this line. That's not exactly how I wrote before, but you get the idea. All right, so you got the momentum. Okay, so I want to solve for this. Or actually technically, no, that'd do the job. Well, I have to solve for, no, that's fine. That's what I need. I've got the radius, I've got the B, I've got the Q. I don't think I actually need to input in the mass of the electron by the looks of it. I've got B, I've got R, and I know the charge of an electron. So let's give it a crack. All right, so times 10 to the minus 4. Blah, 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 times 2.31 Tesla. And then Q is 1.6 times 10 to the 19. Okay, so my calculator is not loading on me. Why are you not doing that? Right. Got the loading screen. It's just on my backup screen. Let's quit out of all that. And clear. All right. So what do we want? 1.46. So I'm not used to this configuration. All right. What's for? Times 2.3. 1 times 1. I wrote 1.9, it's 1.6. I'll fix it up in a sec. Times, I should say, let's use the scientific notation way of doing it. Minus 19, you make less mistakes that way. Okay, yep, approximately right. I'll just fix that up. Okay. And what do I get? I'll keep it on the screen at the same time, can I? Okay, yeah, it is correct. Okay. Okay. Now calculate the wavelengths of electrons with the momentum of that. Okay, so assuming you weren't able to do that before, you can do it now. So let's work out this one. Okay. Right. Bit rusty on this. Let's remind ourselves again the Rockley wavelength formula. It's down. Yeah, this is a rearrangement of that. Okay, so we've got momentum. We just need Planck's constant. Rearrange that. So it's h on p. Okay, lambda equals h divided by p. All right, so that is. All right. Just remind again, your Planck's constant can be found in here. So there it is, 6.63, 10 to the minus 34. Divided by. A reminder, if you're Puritan about your mathematics, you'd have to do it like that. Yeah. Although I'm going to do it with scientific notation, which will do that automatically. We'll just remind you of that. A lot of people still make mistakes with that stuff. Take our last answer, just put it in. Okay, so I imagine it's going to work. So if I take this, This is this is a floating point number. It's just one number, no operations. So if you just do divided by, now if I take my last answer, should have the correct result. Yeah, I can see that's kind of that's in the ballpark because of the I can look at the powers and say, yeah, that looks like a division. You've got a very small number and a rather small number, and you've got a small number. All right. Yeah. So yeah, if you misinterpret the division, you'd end up with something that's even smaller than minus 34. There's really only two ways that this can work. If you do it right, or you stuff up the division because that's not counted in part of the division. And we're okay. So in that case, all right, there we go to answer. So, well, we're going to have to memorize it and then write it down. 1.23 minus 11. And it also looks correct because it's in the bandwidth of, that's the bandwidth about the wavelength, I should say, of X-rays. Is about 10 to minus 10, 10 to minus 12. So that's in the ballpark what we're looking for. Okay, so that was question one. Let's move on. All right, so we've got electric field. All right, we're entering perpendicular to the field. An electron is entering, more specifically, enters a uniform electric field provided by applying a potential difference of, okay, we've got one piece of information there, 150 volts. And place in vacuum. You got distance d, length of the plates, and initial velocity. Okay, not physics of gravity. All right. So I've already gone and described that one. Okay, the path is parabolic. It'll come in. Well, you see, you've got it drawn there. It's going to go parabolic. Oops, it's a little bit too straight. So I freehand draw. I'm left-handed, but I'm used to using the mouse in my right hand. So I have, I'll do the best I can, basically. I'm going to have a hard time drawing this curve. It's meant to be parabolic. You get the idea. Or maybe you don't. All right. One more try. Let's just make it slowly. Let's look. Okay. Okay, so that's something like a parabolic curve. Okay, something like it. I'm doing my case to determine this it's leaving without a hidden plate. So it should be getting steeper as it goes. So it's rather wide parabolic in the way that looks. Okay. Show the magnitude of acceleration. Uniform field is that. Okay, so we're going to show that answer. All right. So we've got 150 volts, and we got a distance between the plates will be important, and the acceleration will be important. So we also need the fact that we have an electron. The velocity is not important in this section. So, okay, part B. Let's go back to our equation sheet and see what stuff we need. Okay. All right. So magnetism. Okay, E equals VD. All right, we go down that path and then work out the force. So with that one, and then work out acceleration. All right, so what we're going to do is work out. All right. So we have. The other E was one voltage. Delta V on D. Okay. Remember, force is also mass times acceleration. So I'll write it as force first. So force is equal to delta VQ on D. And then acceleration, you divide the mass out from that. So you'd have delta V Q on M t. All right, and that's equal to, all right. I'm just going to type this out. I'll type it out and draw a line underneath it. How about that? Okay, so we got 150 volts times Q is 1.6. I forgot. I remember why I don't like doing it this way, because I have no power symbol. 1.6 times 10 to the. I'll just write tilde. No, it doesn't even like that. Minus 19 over. Mass is 9.11 times 10 to the power minus 31 times by d, which is 0.050 meters. Okay, so and then we're going to divide that. Okay. And we should get the answer. Let's just see if it works. Okay, so all right, bracket 150. You need a bracket for this. You got multiple things multiplying, dividing. It's just not going to work otherwise. All right, times 1.6 minus 19. C's 31 times 5 point. Boom. Okay. Was that right? 5.27 10 to the 14. Yeah, to that. Okay, so that's all right. 5.7 times 10 to the 14 meters seconds minus 2. Cool. All right, time taken for the electron to pass through the uniform electric field. Okay, that is the horizontal component, so that's easy peasy. All right, so that is, okay, we have a distance, we want a time, and we have a velocity. So remember, all right, so you want time. All right, distance divided by velocity. Okay, so that's the L, length, divided by the initial velocity. Okay, so you had L, 0.1. All right, divided by 1.10 to the 7. Slow minus positive. That's very slow. It's actually very fast. Okay, so I think that'll be 10 to the minus 8. Double check on the calculator. Bit rusty and being coming off holiday mode. Yep, 10 to the minus 8. So yeah, 10 times to the power minus 8. That's what that reads as. Okay, so that's 1 times. I know writing it with the 1 times is kind of redundant, but it's still scientific notation. Should probably write it as 1.0 to be honest. Seconds. Okay, that's all you had to do. So there was no component. So there's a component of that. Okay, no, actually. Sorry, I just worked out something I didn't need to work out. So I wrote that question wrong. So I said the time taken. I just worked that out. I just worked out what they just gave me for free. That was silly. Oh well. Oh, actually, I didn't. I can still keep the parentheses. No. So, well, at least I proved it. Okay. So I didn't read the question right. So make sure you always read the question right. All right. I did have to do a harder part. Okay, so they did the easy part. Okay, so you got the time. All right, determine the direction and velocity of electrons that leaves the uniform magnetic field. So I need to work out okay, so I have the horizontal component. I need the vertical component. All right, so what I'm going to do, okay, so I'm going to work out velocity final velocity is equal to, so think about your equations, you can go back to your sheet if you're rusty on your parabolic motion. So these are the ones you can use for uniform acceleration, which is uniform direction acceleration. So what do we have? Okay, we can actually use we can use the first one because we have the initial velocity is 0 in the vertical direction. We worked out the acceleration for the previous part, and we have the time. Okay, so we have v equal v naught plus at. All right, equals 0 plus, that round to 5, I'm just going to use the values they've been giving us, 5, 3. So you effectively can do this question just based off of the show that from in the information. So this question can be done completely independent of the other ones because you can just do this, which is two values they've given you for free. Right, I can read what that is straight away. It's 5.3 times. Yeah, because all I'm doing is times it by 10 to the minus 8. This brings that one down to power 6. All right, we're not done yet. Time for a vector diagram. All right, so we have okay, I'll draw like this. All right. I wish I had line drawing tools on here. Maybe I should have used Paint instead of Microsoft Edge. Okay, so we have now this is the short part. 14 minus 8 is 6. And then this part is 1.0 times 10 to this. So this is almost twice the other one. Because I could write that as like 10 and in the ratios it would be 10 and 5.3 times 10 to the 6, both cases. So we need to work out this. We need to work out the direction of velocity. So we just okay. So read the question again. Determine the direction of velocity. So we need to have a direction. We need to work out theta, an angle in there. Okay, we do that with inverse tan. Theta. That's opposite. Lazy, so I'm just going to write it that way. Yeah, so like I said, that's basically 5.3 divided by 10. So when you cancel it down, sorry if I just do it like that. You can do it the full way if you want to check for yourself. Do the inverse tan of that. So we have an angle of 27.9. Okay, so equals. And we can just. What's a little improvement? There we go, degrees. Okay, there we go. All right, now I've already actually filled in the last question. Explain why the motion of the proton. Okay. Actually, sorry, that is. I just did question 8. Sorry, that is for question 9C. So this is a similar question. Proton is fired horizontally in the vacuum halfway between two oppositely charged parallel conducting plates. Speed of that, shown in the diagram below, the plates are 50 centimeters long, and yeah, very similar question. All right, volts per meter, uniform electric field, directed downwards. All right. Time of flight, photon, same thing. Okay, let me undo that. I can't undo that, can I? Can I move this though? Yes, I can. Alright, so I'll move that down here for later. Alright, come to that one later. Alright, start 9A. Time of flight. Same thing, basically. Time equals the length of the plates divided by the velocity of going in. So what are the lengths of this one? 15 centimeters, so 0.15 meters divided by 7.2 times 10 to the 5. All right. Yeah, it's to show that question, and we got it right. All right, so I'm just going to use their answer. Because you get the mark for setting up that part. Okay, so calculate the vertical deflection. So we've got a different equation to work out now. Okay. Proton, when it's in a uniform electric field. Okay, so the reflection, this is a vertical component. So S, I would use this equation, V naught T plus half AT squared. Okay, so, but think about that equation, we need to go work out A. So I'm here part B. Cut myself out a little space. That is all part A now. Let's not do that. I should also write. Let's answer the question quickly. Okay, so we've got that. Okay, so A is equal to, okay, F on M, but is EQ on M, so E, and we're given the electric field strength, not the voltage. Okay. This is the proton this time. Proton, okay, so we have, what was it? Okay, 1 times 10 to the 4 times 1.6 times 10 to the negative 19 over, okay, now what do they actually use in the former sheet for protons here? 1.67, okay. Older versions used to be a little bit more precise with this. 10 to 27, that is right. Yep, 27, yep. Okay, so we'll go calculate that in a sec. Okay, this part cancels the 0 because there's no initial vertical velocity. So just be mindful of that. We already get the deflection here. Okay, and that's all we need to do. We just need to work out A and then substitute into here. So we'll finish off this in a sec. All right, work out A first. All right. Okay, so bracket. So yeah. 1E4. Divided by. Now this only works for them using this particular scientific notation method. Otherwise you need a bracket around the denominator as well. Because that resolves the numerator, this bracket here resolves the numerator to form one number, and this is one number, so you have a division of a numerator and a denominator value only. Okay, so that's fine. Okay, so we get 5, 8. What was the order? Okay. I can't use this. Oh no, yes, I can. We solved for time. So I thought we hadn't solved for time. We did in part A. Okay. Times 10 to the 11 times, okay, times bracket. Oh boy. Yeah, we did that earlier. Let's just show that anyway. So yeah, this one is 4 marks, so there's multiple sections you have to do to get this right. 10 to the 7 squared. Okay. All right, so I've already got the acceleration here, so I'm going to times that by 0.5. That's that part done, and then times it by the time squared. I can do that like this. About a drama. That will work. Yep. So you're looking at about 2.1 centimeters. So let's try it as. All right. Come back here. Where'd you go? Come back to me. There you are. I don't need that big. Right. Anyway. Yep. Yeah, that's all you need to do. All right. Explain why the motion of the proton is similar to the projectile launched horizontally in the surface of the Earth. Both events uniform downward acceleration, thus a parabolic path. Okay. Yeah, my worded questions are quite concise, but I got the key points in there. If you want to put more detail into that, that's fine. Okay. Sketch path of electric fields. Oh. These are meant to be parallel, equal distance, and straight. Now, there's another keyword in there. I did read this earlier. Yeah, sorry, mine are not going to be straight, particularly because this scan is diagonal. I didn't have to draw that many of them either. Oh well, I've done it now. Nearly done. All right, so these are meant to be parallel, equally spaced, but there's another keyword there, finite. Why they're finite? Got to do the edge effects. Okay, so these ones are curved. And that should do the job. Okay, all right, that's all I have to do for that one. All right, so for 3 marks, yeah, uniformly spaced, parallel, yeah, pull your rule around if you want to and just make it neat as you can, just enough for them to do it. And the 3rd mark would be these edge effects where you get that bending of the field at the termination of the bum of the parallel plate. Okay, all right, xenon ions mass that. Assuming I can't read that too well, assuming it's minus 25, I'm going to go with that because that sounds about right. Enter a, I suppose I could just Google it. In kilograms. Not the density. Mass is xenon. Yeah, it won't. Yeah, look, it's minus. I'm pretty certain it's minus 25. We're talking about atomic mass, so you're talking about like okay, the number of roughly there is a equivalence like this is a different unit. So what is atomic mass? Yeah, so it's like all the way around. Yeah, yeah. Well, it's going to be order minus 25. I'm certain of it. Okay. Oh, okay. Let's say that one's not losing anything. Yeah, so it's minus 25. 25. Okay. Enter the electric field in a small hole center upon the plate. So you're going to have these ones are going to go through. You get a small hole there somewhere, and you're going to have the xenon going down, accelerating that way, and presumably leaving through another hole. Okay. And we've got a voltage. Alright, so work out the voltage. Okay, so for gain of kinetic energy is delta V times Q. Difference times Q equals so these have got a single positive charge. We all right. So times righty, that should do the job. Okay. So 2.1 is 4. 10 to the minus 16. Boom skis. All right. Yep. All right. Show that increase the speed of one of the xenon ions is this. All right. Well, okay. You can rearrange your EK formula. EK formula starts off looking like this. B squared. You can divide the mass across times by 2 to get rid of the half, and then take the square root. So you basically end up with this 2 E 1m inside a square root. Okay. So we just worked out that. So we know 2 divided by, okay. They have a massive radius of 1, we were discussing before, so that 2.1, and that's definitely minus 25. Okay. And then take a square root of that. I'm just going to use the power of a half as a stand-in for that, for the way I'm writing it. Mm-hmm. Yeah. Shut up. Nice. 0.1. E minus 16. I'm going to do this in steps. I'm just going to take my last answer and then just do the next part. It's just doing it, trying to put this all together is just going to get messy. You can do it. It's and you can structure it and make it look okay, but it's just time consuming and annoying. Okay, so we've got that. Seems about right. And then we're going to take the square root. Power of 0.5 will do. And 2 times that divided by that. Yep, that should be right. So about 4.4 times 10 to the 5? Is that what I said? Yep, no, 10 to the 4. Yeah, that's right. That's 10 to the 3, 10 to the 4. Yep, that's right. All right, 4.4. Now they'll mark, if you set it up correctly and you're getting it, like if it rounds off, you can write this. I'm writing it the way they write it just to save a bit of time. Okay. Calculate the magnitude of change of the momentum of one of the xenon ions. All right, change of momentum. Now that's effectively 0. Assume it doesn't come in with much mass, so basically it's going to be what we just worked out there. Times by the mass, so that's a V and then M. I know it's MV, VM, same thing. So I just wrote that number first because I could see it first. All right. E minus half. Okay. Done. Right. Was I sure that? Or was it? No, that's it. All right. So. Let's write that at 9.7. Take newtons. Okay, squeeze it in. All right. Now, last question. Xenon ions accelerate by an electric field used to increase the velocity in the straight line time spacecraft. Explain quantitatively, so like kind of without math. In terms of the law of conservation of momentum, the increase in velocity of spacecraft resulted in the emission of excrete xenon ions assume in the effects of gravity inertial. All right, so from this comes, you can go right back, if you really want to go back, you can talk about, okay, so Newton's third law, so equal and opposite forces. The force on one is the force on two. And if you remember that momentum is, so like delta P, I also can change the kind of the theme of this. So the delta P on delta T, which is force of xenon, is equivalent to the negative of the rocket change of momentum. So I get R for rocket on delta T. So same time interval. You can cancel your delta T's. And that's another way of expressing locum is delta P of xenon is equal to delta P of your rocket in the opposite direction. So it's a minus in there. I'm going to draw some vectors on this one just to make you happy. Happy vectors. Happy vectors. Okay. So thus, now I'd probably at least write that statement. There's other ways in the general locum idea that you can explain it, but the idea, like I find this rocket and exhaust gases, this is the easiest way to express it. Thus, the rocket must accelerate in the opposite direction of release xenon charge with same change of momentum. And then you can follow on and say, basically, if there's a change of momentum and ignore that we've shut off a few atoms here and there, the rocket is accelerating, so it's gaining velocity. Okay. All right. So, okay. Bit more to do. All right. Okay. Electrons moving constant velocity of that, midway through two opposite charged points that uniformly was restricted planes of that. Just over to that ones. Okay. Oh yeah, it's very repetitive, these ones. So that doesn't take the path. 2 centimeters. Okay, so that's 11A. Okay, so you have time equals distance, but just write it. Distance on V equals, okay, it is 4 centimeters, so let's convert that to meters before we forget. Divided by 2 times 10. Yeah, so I'll do 10. Now, if you divide 0.04 times 10 to the 2, divided by 2 would be 0.02, and so that's already 2 times 10 to the minus 2, and then that makes 2 times, you're checking the calculator, but it is 2 times 10 to the minus 9. I'll do that in my head. Check it, but that is the answer. Show the magnitude of the acceleration electron is moving in the electric field. Okay, we have another electric field strength one, so acceleration can be expressed as, we've done a few of these already, so we just go through it. E, Q on M. Okay, and we are we've got electrons, so that is, okay, we've got 2 times 10 to the time. $17 over 9.11 times 10 to the negative 31. All right. Do that one. This one should be fine to do in once. Yes, because it's times divide. If we write in scientific notation, it will work. Abundance of caution if you so wish. But this one will work. And let's just show that. So to 3.51 times 10 to the 15. Yep, 3.5 times 15. Oops, that was B. Oh, a nice acceleration. But it is question B. Okay. Writing A for acceleration, not A for motion A. There we go. Okay. Calculate the magnitude the speed of the electron has moved after it's moved. So we're solving for the speed component, so we need two components of motion here. All right. After it's moved 4 centimeters. Okay, so basically at the end of its time of flight. Did we work that out? Yes, we did. Yeah, that's there. All right, so we need the vertical velocity. That's cancelled. That's 0. Right. Check on your calculator, make sure I've got this right. It's getting a bit lazy. Well, I'm taking shortcuts, I should say. So that's 3.5 times 2 is 7, and then we got 10 to the 6. All right. Then we've got 10 to the 6 down and 2. Interesting. So then this one is going to be going like that. And that. It's 2. And 7. I want to work out the speed here. So this is also that's Vy. That's V. And V. Let's work it out with Pythag. No, I'll do it here. This time's a bit squishy. Okay. Right. I won't take shortcuts with the calculator. I'll just show you the proper way. Okay, let's just work them out. So sums the squares. All right, bring it up to E6 squared plus 7E6 squared. And then take the square root. Power of 0.5. All right, so that is 7.3. Yeah, it's consistent in the notation sense. All right, last one. Okay. So running for nearly an hour. I'll leave the video here. I'll pick up from question 12 later on. So there's been a long one so far. A little bit of my stuffing around, but we've got a bit more to cover. All right, so I'm going to leave this video here because it's getting very long. All right, stop recording now.